Okay, so if you guys can do me a favor, so we've already talked about formula mass and also molecular mass. So the way that we're going to actually determine that is by first recognizing how to write the chemical formula. So if we have sodium nitrate, we know that we have a total of 1 sodium. What is the charge on sodium? +1, that's right. And then nitrate, we know, is also going to be what charge?
-1.
-1. So we know that there's one +1, one -1. And we know that any ionic compound, when it comes together, it has to be equal to. So we're going to basically write it as sodium nitrate. Okay, NO3. Okay, so now that we know this, right? Now that we know that we have the chemical formula, we can calculate the molar mass by using the periodic table. So everybody has a periodic table available. Let's see, pull up one. See, all my. Okay, so we have sodium nitrate. So how many total sodiums do we have?
1.
We have 1 sodium. And sodium weighs how much?
22.99.
Okay, so we can round up to 23, make our lives a little bit easier. How many nitrogens does sodium nitrate have?
1.
And nitrogen weighs?
14.007.
Okay, so we could just round up to 14. And how many oxygens?
3.
And oxygen weighs?
60.
Multiply that times 3. So then we can add those together. Get 85 grams per moles. Now, the units that we're using are going to be dependent on what we're looking at. If we're looking at something that we can see visually, we're going to put it in grams per mole. But if we're looking at a single molecule, so if we have a single compound of sodium nitrate, then we're going to use the unit AMU for atomic mass units. So often when we're looking for that term AMU, or we're looking for that type of unit, they're going to ask you for what we call the formula mass or the molecular mass. When they're looking for the units grams per mole, we know that we're making reference to grams per 1 mole, and that mole being a quantity, right? So we call this the molar mass. Or sometimes we get lazy and you'll see it written as the mass, which is totally incorrect, but it does happen. Okay, so if they ask you for the molar mass, you're going to be giving me grams per mole. If they ask you for AMU, you're going to be giving me, or if they ask you for atomic mass, or the formula mass, or the molecular mass, you're going to be given the AMU, or just units. That's the other way to it. Just okay. Questions, concerns, Cash? Okay. Okay, so the next one is, how many atoms of each element are in the formula unit of ammonium carbonate? So first thing I want to do is to do what?
Write it out. Compound.
Okay, so the formula.
The formula, NH4 for ammonia.
And then what is the charge on ammonium?
1.
+1. Okay, and then carbonate,
CO3.
and what is the charge on that?
-2.
Okay. So how many ammoniums am I gonna need?
2.
And then how many carbonates? Okay, piece of cake. So now give me the formula mass. Okay, how many nitrogens do we have?
2.
And we know that each nitrogen weighs
14.
2. Okay, how many hydrogens do we have?
8.
And each of the hydrogen weigh
1.
How many carbons do we have?
1. And 12.
Okay, and then how many oxygens do we have?
3.
And oxygen weighs
6.
okay. So we're gonna add those all together.
Six.
Okay, so what unit should I use since I asked for the formula mass? Okay. Questions? Oh, there are 5 questions. Okay. So again, formula mass is for AMU, and grams per mole is when we're talking about molar mass. Okay, so when we're making reference to molecular mass and formula mass, they essentially kind of mean exactly the same thing. The only thing, molecular mass is when we're talking about covalently bonded compounds, because it forms a molecule. Formula mass usually makes reference to an ionic compound. And what do I mean by that? And let me show you. It's easier for me to show you that. Okay. So for instance, if we have carbon dioxide is covalently bonded. It forms a single molecule. They all are interacting with each other. So we would calculate its its molar mass because it's a molecule. Okay. Even though that an ionic compound would also be, quote, a molecule by definition, it's not considered to be, when we're making reference, the difference between molecular mass and formula mass. It's not one unit, it's the average of a unit. Okay. So if we're calculating the molar mass of carbon dioxide, the molecular mass of carbon dioxide, it's going to be, we have two oxygens, which are both going to be 16 units, and then we have carbon, which is going to be 12 units. Altogether, that's going to be 44 units, or AMU, atomic mass units. So, if we look at the formula mass of ammonium nitrate, first off, what is the chemical formula for ammonium nitrate?
NH4. NO3.
We know that the ammonium is going to be +1, and the nitrate is going to be a -1. So when we bring them together, you're only going to need one of each. Okay. So what would be the formula mass of ammonium nitrate?
So there's 2 nitrogens.
Two nitrogens.
14.
14 times 2.
4 hydrogens. One each.
Okay, 4 hydrogens. Each one weighs 1.
And 3 oxygens.
Oxygens, and then each one weighs
16.
So we multiply them, add them all together. Okay, so what is going to be the units?
Yeah.
Okay, piece of cake. Excellent. Online agrees with you as well. Okay, so if we talk about the mole, we've already been introduced to the mole. We know that 1 mole is going to be equal to 6.022 times 10 to the 23rd. This is called Avogadro's number, and it's also called Avogadro's constant. We basically use the mole to let us know that that is the quantity, right? Now, the mole was based upon 12 grams of carbon, 12. Carbon 12 is that isotope that weighs 12 grams, right? So when they weighed out 12 grams, they calculated the number of carbon atoms that there were, and that's how they ended up with Avogadro's number. So knowing that, we know that a mole is going to represent quantity, okay? So often, if we are talking about that quantity, and somebody tells us that we have a sample consisting of 0.25 moles of ammonia, how many atoms, or sorry, how many molecules of ammonia do we have? How would I calculate that? So what do we know about the mole?
It's 6.02 times 10.
So we know that 1 mole is going to be equal to 6.022 times 10 to the 23rd. So we know, kind of like a dozen. Today we ate a dozen bagels. How many bagels did we eat? Well, because we know that a dozen is 12. A mole is like that dozen. Only thing, a mole is 6.022 times 10 to the 23rd. Okay, so if I have 0.25 moles of ammonia, how many molecules of ammonia am I going to have? So we're just basically going to set up a dimensional analysis. Starting off with 0.25 moles. Okay, so we know that 1 mole, and here we have moles. We're going to want to get rid of moles, so we're going to put moles on the bottom down here. That's going to be equal to 6.022 times 10 to the 23rd. That's molecules. No. We want to make sure not to mistake a mole for a molecule. We want to make sure that we're using the abbreviation appropriately, because they're not the same thing. Okay. So if we do that math, how many sig figs should we have? 2. Okay, questions? No questions. Concerns? Okay. Okay, so again, when we talk about molar mass, that's going to be based upon carbon 12. So we know that carbon is going to weigh 12 atomic mass units. And then we also know that carbon, 12 grams of carbon is going to be equal to 1. So calculate the molar mass of calcium fluoride. First off, chemical formula for calcium fluoride, Lauren. Right there. Carol? I guess they all left.
Hold on, I do have it written down.
Okay,
Yeah, or actually, no, it's not CAF4, it's CAF2.
CAF2, that is correct. Okay, and we know this. And we know this because calcium has what charge? Calcium has what charge associated with it?
Positive?
Yeah, plus what?
2.
Plus 2. So we know that the calcium is plus 2, and then we know that each fluorine is going to be minus 1. So we'll need 2 of those to balance out. Right? Okay, so now that we have the chemical formula, how are we going to utilize the chemical formula?
You have 1 calcium that weighs 40.
Okay, so the 1 calcium that weighs 40.
2 fluorine that weighs 19.
And we have 2 fluorine that weighs 19. We add them together. So then what would be the units? Fidel?
Give me a sec, working on it.
Okay,
There it is right there. Yeah. So 19 times 2, and then you add those two with the 40.
okay.
Yeah.
So we get 78. 78 what? What are the units?
Grams
Um,
per mole.
Yeah. GM, smaller mass.
That's right. Okay. Thank you. Man, it's so easy when you have a class of 5. It's perfect. Oh, get carried away. Okay, so in this slide, all of the different atoms, which are shown in figure 8, that basically they all have 1 mole in terms of its quantity. Now you'll notice that they weigh different because when we think about quantity and mass, they are not the same, okay? And we don't want you to misunderstand it. So if you guys think about an apple and a grape, do an apple and a grape weigh the same? No, right? In most cases, the apple is like 50 times bigger than the grape, right? And so it's the same thing, but in quantity, if I have 1 apple and 1 grape, isn't that the same quantity? Okay. And so that's the main purpose of this slide here, is to show you that here, this is exactly the same quantity, but you're going to have different mass associated. Okay. Okay, so you're carrying out a laboratory reaction that requires 0.0360 moles of barium chloride. How many grams of the compound do you measure out? Okay, so when you're faced with a situation like this, you're going to always start off with the given. So what would be my given under these circumstances?
Then you have 0.036
Your quantity.
Okay,
barium.
so we're going to have 0.
0360.
Okay. And you said moles of barium chloride. So what is the chemical formula for barium chloride?
BaCl2.
BaCl2. Okay. So what is the molar mass of barium chloride?
Barium weighs 137.
Okay.
And then chlorine weighs 35.
We're going to actually use the 0.45 because it's so close to that catching point, right? So we're going to multiply that by 2. Round it up. Okay, so we have 2.8 grams per mole. So we're given moles and we want to get mass. So what do you guys think we're gonna do with that? How will we get rid of moles? Moles on the top or on the bottom?
Bottom.
So we know that this is grams per 1 mole. So that means we have 1 mole in the bottom. And so we're going to put that 208 on top. So moles are going to cancel out. How many sig figs should I have?
Three.
Okay. Okay, questions? Concerns? Cashola. Okay. So if we're given units, we're going to use Avogadro's number to get to moles. If we're given moles, we're going to use molar mass to get to mass, and vice versa. Okay, so we should be able to go from units or quantity to mass. And this is just basically showing us the same concept. So if we're given mass in grams, we're going to use the molar mass. We should be able to get the number of moles. If we have the number of moles, we can use Avogadro's to get the quantity. Okay. So determine the mass in grams of 3.2 times 10 to the 24th molecules of sulfur tetrafluoride. What is the chemical formula for sulfur tetrafluoride?
SF4.
Okay, so if I have 3.2 times 10 to the 24th molecules of sulfur tetrafluoride, how can I get to mass? So what are 3.24 times 10 to the 24th? Is that quantity? Is that moles?
Quantity.
It's quantity. Okay. So what do I know if I want to go from quantity to moles? What am I going to use?
The 6 point or the Avogadro's number.
Times 10 to the 23rd. Funny, I had a student that would always call it avocados. That's the first day that I introduced it. I spelled avocado instead of avocado. Not letting it down. Okay, so that's going to be 1 mole. Okay, and then how can I go from moles to mass?
Get the molar mass.
We need the molar mass. Okay, so the molar mass for sulfur. How many sulfurs do we have?
1.
Okay. What is the mass?
32.
And then how many fluorines do we have?
4.
Sorry.
That's all right.
19.
Okay, we got them together. Here are. So we get 108 grams per mole. So are moles going on top or bottom?
Top.
Sure.
Oh, mole, yeah.
So moles are going to go on bottom. So we're going to put our 1 mole on the bottom. And then on top, we're going to put 8. How many sig figs should we have?
2.
$570 grams. Okay, questions? So Edgar, do you have any questions? Yes. Okay, let's move forward. Okay, so if we talk about percent composition by mass, so we're going to be talking about the part over the whole. So if we have a pie, and let's say the class here eats 2/3 of the pie, right? So the part would be what? And what would be the whole? In that case.
And
Pie and
2/3.
whole.
Okay, so the 2/3 would be the part. So basically, of the 3 pieces of pie, we ate 2 pieces of it, right?
Yeah.
And so the part would be those 2 pieces that we ate, and then the whole would be
The pie.
all 3 pieces of the pie, right? Because 3 makes a whole. Okay, so that would be the part. Okay, so when we're talking about a compound, we're going to be talking about one part of that compound, right? So in this case, let's calculate the percent mass of fluorine in calcium fluoride. So the part in this case is going to be the fluorine. The whole is going to be the calcium fluoride. Okay, so we know the chemical formula for calcium fluoride is
CA.
we know that the calcium was it weighs how much?
40.
And we know that the fluoride,
19.
each one weighs 19. We know 19 times 2, 38. And we add that together, and that's going to give me my whole. Okay, so if I want to calculate the percent mass of fluorine in calcium fluoride, all I'm going to do is take the mass of the fluorine, which is
30.
and I'm going to divide that by the whole and multiply it times 100. Okay. $38 divided by 78 times 100. 48.7. Okay. Question? Piece of cake, not too bad. Okay, so calculate the percent composition by mass of aluminum sulfate. So we want to calculate each percentage for each of the elements that are in aluminum sulfate. Okay, first thing that we want to do is to do what? Write the chemical equation or chemical formula, sorry. Okay, so the chemical formula is
On it, Al2, SO4, 3.
Al2SO4. And SO4 is going to be in parentheses.
Yeah.
3. So why is it Al2SO4?
Because aluminum is +3,
Okay.
and then sulfate is 2-.
Okay, because aluminum is going to be a +3. And then the sulfate is 2-. So for them to balance out, I'm going to need 2 aluminums and 3 sulfates. Okay, so how many aluminums do we have in aluminum sulfate? We got 2. Okay, and aluminum weighs
27.
okay. Times 2. How many sulfurs?
3.
Sulfur weighs
32.
and how many oxygens? 12. Oxygen weighs
16.
So we're going to add them all together. Okay, so then how would I calculate the percent mass of aluminum and aluminum sulfate?
Divide its mass. And have a molar mass.
We're going to divide the mass by the total mass. So we have 54 divided by 342 times 100. %. Okay, what about the sulfur?
$96 divided by 342 times 100.
1%. Okay, and then how would I calculate the last one? What is the easiest way?
192 divided by. Or you can just add the other ones.
So we could just subtract the other ones. Okay, questions? Concerns? Okay, let's move forward. Okay, so it says aluminum chlorate is 38.35% chloride. What mass of aluminum chlorate is needed as a source of 50.0 milligrams of chloride? Okay, where are we going to start? What is the definition of percent mass again?
What amount you have of that element in the whole compound.
Okay, so it's the amount of that element over the whole compound. So we're talking about, we want chloride over aluminum chloride. What is the chemical formula for aluminum chloride again?
ClO3.
And how many of them do I need to balance out aluminum? 3. Okay. Multiply by 100. And that's going to get my percent mass. Okay. So don't we have the percent mass for the chloride? So let's go ahead and plug that in. Don't we have the mass of our chloride that we want to have? So plug that in. And so we don't know the bottom. So I'm going to use a symbol Y here. Okay, so we're going to solve for it. We're going to solve for Y. So we end up with 50.0 milligrams over 38.35 times 100. That's going to be my Y. So how many sig figs should I have? 3 sig figs. That's correct. It's going to end up with 134, 1.3 times 10 to the second power. That's milligrams. Questions? What's that? Beef and peppers. It's got a little kick. And Mexican rice. Yellow rice. I love yellow rice. Delicious. I like vegetables. Being a fan of vegetables. Okay. So you guys feeling okay with percent mass? Percent composition mass? Okay. I would say I have the best students. My students always speak. That's how I got so fast. Yeah, that is it's the genes. Okay, so the next thing is empirical formula. Man, we're definitely pushing through this. 5 students is a perfect number. I should tell West Hills that we should always run classes with 5 students. I can have tons of sections. Okay, so when we're talking about empirical formula is going to be the simplest formula that we can have and maintain whole numbers. So you're going to take the chemical formula and then you're going to try to find the lowest common denominator. Okay, so if we have a formula, a molecular formula of C4H10, what would be the empirical formula?
C2H5.
Okay, so we can divide both numbers by 2, and then we're going to end up with C2H5. Okay, piece of cake? No problems? Okay, so let's say we have glucose. Oh yeah, go ahead. Take what you need. As long as it comes back.
Yeah, I'm taking that home, you know.
Yeah. I know you like it. They're fancy. So, why my computer's trying to shut down? Okay, so my computer may shut down in a few minutes. If it does, then we don't have control over it. So chemical formula for glucose is C6H12O6. So what would be the empirical formula for that?
H2O.
Okay, so it would be CH2O. Okay, simple, not too hard, right? Now, empirical formulas become important when we start talking about analysis, right? So a lot of times the equipment that we get, it doesn't give us the molecular formula. It'll actually end up giving us the empirical formula. So we'll need to sit there and know how to use that empirical formula, the simplest form, to sit there and get to the molecular formula. Okay, we'll talk about that a little bit. Okay, so now if we look back at those numbers, right? So we're talking about C2H5. How many carbons do we have?
2.
How many hydrogens do we have?
5.
Now, is that quantity or is that mass?
It's quantity.
It's quantity, okay? So we want to remember that we're talking about quantity. So when we're talking about quantity, we're going to always want to get to the number of moles, okay? So we're always gonna use the number of moles to help us figure out that quantity. Okay, so if we have a sample of a pure compound made up of 1.61 grams of phosphorus and 2.98 grams of fluorine, find the empirical formula of the compound.
You're
Okay.
gonna divide 1.61 grams of phosphorus by its mass, which is 31 or 30.9.
31. Okay, so we have 1.61 grams of phosphorus. So we're going to divide it by its molar mass, which is 31 grams per 1 mole. We got that again from the periodic table. So it gives me what?
0.0519 moles.
0.015.
Oh, no, 5.1.
Oh, okay. Okay. And then for the fluorine, what is the molar mass of fluorine?
19. Now, once we get to this point, what we're going to do is we're going to take the one that is the least, and we're going to divide both of them by that number. So which one is smaller, 0.0519 or 0.157?
0.0519.
Okay. Okay, so we end up with 1 phosphorus and approximately 3 fluoride. So then our empirical formula is going to be PF3. Okay. Questions? No questions? Questions? So. go on then. Take our break after the next slide. We'll make it short, since you guys never take breaks anyway. You want to take a break today? Like today, I'm gonna take a break. Okay, so if we have nicotine is 74.1% carbon, and this is percent mass, and 84.64% hydrogen, and 17.3% nitrogen, what is its empirical formula? So again, this is percent mass. So what is an assumption that we can make about the nicotine?
It's mostly carbon.
Okay, so it's mostly carbon. So is there, let's assume that we had 100 grams of nicotine.
74.1 grams of carbon.
Okay, so if we assume that we have 100 grams of nicotine, so then we know that 74.1 gram is going to be carbon. How much of it is going to be hydrogen?
8.64 grams.
And then how much of it is going to be nitrogen?
17.3.
Okay, so we have mass. How do I get to quantity?
It's divided by its molar mass.
Okay, so let's divide it by its molar mass. So what is the molar mass of carbon?
12.
Are you guys there? Can you hear me?
Hello?
Yeah, it restarted. So let's go ahead and take a break while my computer decides it's gonna start back up. Okay, last we left off. We had 74. 1 grams of carbon. You told me divided by 12 grams. Correct. That's going to be 1 mole. On top. Okay, and we know that we had 8.64 grams of hydrogen. What is the molar mass of hydrogen?
1.
1 gram of hydrogen, or 1 mole of hydrogen. And we had 17.3 grams nitrogen. You can use all of those. Those are dentist gloves, the thick gloves. Yes, oven mitts, we have it all. Make it work. I don't want to give them your silicone. Hot thing to handle. Okay, and we know that nitrogen weighs 14 grams. Okay, so what do we do next?
Divide them by the smallest number, which is 1.23.
So we're going to divide everything by 1.23. So we get C587. Piece of cake. Okay, so let's do a problem that's on your. Maybe. Sorry, computer's running really slow right now. Just realized I didn't watch your homework. Too nice sometimes. Okay, it says a compound that contains only carbon, hydrogen, and oxygen is 68.5% carbon, 8.63% hydrogen. So what is the empirical formula of the substance? I might not forget that.
Let's, since it's multiple gas, is there anything that we know that we can eliminate immediately?
B,
Why?
doesn't have oxygen.
It doesn't have oxygen in it, okay? That would make it easy. Anything else? Got rid of B. Anything else? What are we looking for?
Oh, D,
D, why?
because it's not the lowest denominator segment.
Yes, so. So we're able to get rid of those two immediately. Good job. Okay, so we know there's two possibilities, right? So let's see if we can work it out. So what am I gonna do first? What is the assumption that I'm gonna make?
100 grams. of-
So we have 100 grams of our compound. So that means that how much of it is carbon?
68.5.
68.5 grams. And then how much of it is oxygen? I mean hydrogen?
8.6.
And by default, how much of it will be oxygen?
22.8.
You just did that by subtracting. Well, 100 by 11, right?
Yes.
Okay. So we got this first one. So we have mass. How do we get to quantity?
Divided by the molar mass.
So we know the molar mass of carbon is 12 grams per mole. Okay. Hydrogen.
One.
Hydrogen is 1 gram per mole. And then oxygen.
16.
So we know that oxygen is 16 grams per mole. Okay, it's possessed. It's just, it's like, nope, you are not gonna get anything done today. No, I refuse. Okay. Snooze it. We'll see how long that lasts.
I think it's gonna get through the day.
Get a thing.
Okay. Okay, so what am I gonna do next?
Divide all of about 1.43.
Okay, so we're gonna divide everything by 1.43. Okay. 1 oxygen. Okay. Three. Okay, so we get C4, H6. Okay, questions? Okay. So to find the molecular formula, often they're going to give us either the molecular mass or the molar mass of the molecular compound, and then they'll give us an empirical formula. And then we have to use that to sit there and try to find the molecular formula. So let me show you how to go about doing this. A compound with the empirical formula C2H5 has a molar mass of 58.12 grams per mole. Find the molecular formula of the compound. Okay, so we have the empirical formula, which is C2H5. So what would be the molar mass of our empirical formula?
Two carbons, each at 12.
2 carbons, so 12 times 2.
Five hydrogen.
We have 5 hydrogens. So hydrogen weighs, add these together. Grams per mole. So we'll take our molecular molar mass, our molecule molar mass, and we're going to divide it by our empirical formula. Molar mass. Okay, so we get an integer of 2. So that basically means that we're going to multiply our empirical formula by 2. So we get C4H10. Piece of cake. It just stays like this, right? Okay, so next we're going to be talking about stoichiometry. So when we talk about stoichiometry is just basically following like a recipe. So how many of you guys bake cake? How many of you guys have baked a box cake?
Which is not box, right?
Yeah, box cake, yeah. Otherwise, you're making it from scratch, right? Anybody make cakes from scratch?
Yeah, what?
You do? Takes longer? Yeah. Which one tastes better?
From scratch.
From scratch? I don't know. Some box cakes are just so damn
Pretty good.
delicious. Anyway, so if we're talking about a box cake, so we know that we have in a box cake, there are one box requires 3 eggs. Roughly, is that right? Okay. So we know that for every one box, we're going to need 3 eggs. And then that's going to equal 1 cake. Of course, we've got other things to add, but in that concept. Okay. So if I want 5 cakes, how many eggs am I going to need? 15. So basically, we've established a ratio. So if we have 1 box cake plus 3 eggs, it's going to equal 1 cake. That's a yield chemistry. Okay, so this would represent our chemical equation. Like I said, if I needed 5 cakes, we know that we can use that ratio to sit there and determine how many eggs we need, right? So we could always start off, say, we have 5 cakes. And we know for every 1 cake, we have 3 eggs. That gives us our 15 eggs. So we're just using stoichiometry, but we're also just using dimensional analysis, right? So we're just basically counting. So this is going to be the same case when we talk about chemical equations. And often our first instinct is to see, we see a chemical equation, we throw up our hands, oh my gosh, it's a chemical equation and everything like that. As long as your chemical equation is correct and balanced, you're going to be fine. But if your chemical equation is not correct and balanced, you're going to struggle, okay? It's going to be wrong, okay? So the first thing that we want to do is make sure that we have all of the components and our chemical equation correct and balanced. So here we have a correct and balanced chemical equation. So then that basically means that we can sit there and take the ratios of our coefficients. So for instance, for every 5 molecules, or sorry, 5 moles of oxygen, I have 4 moles of ammonia that's going to be needed to react. And I can flip that around. I could say I have 4 moles of ammonia, then I'm going to need 5 moles of oxygen. And then I can also do this with other components or some of the products as well, because I know that for every 5 moles of oxygen, I can produce 4 moles of nitrogen monoxide. Or for every 5 moles of oxygen, I can produce 6 moles of water. Copy this equation, so we're going to need it for our next question. Okay. If 3.2 moles of ammonia reacts according to the equation, how many moles of water will be produced? Okay, so we have our equation down here at the bottom. Ain't pretty. So we're going to start off again with our given. So our given in this case is going to be 3.2. 0 moles of ammonia. So we have quantity, right? We don't have mass. So we can use the chemical equation as is. Okay, so what is the relationship between ammonia and water? What would be our ratio?
For every 6 water, there's 4 ammonia.
So for every 6 moles of water, there are 4 moles of ammonia. Zero. Moles of water.
Piece of cake? Edgar? Are you good? Yes. Okay, so let's move forward. Okay, so this here is just a schematic to kind of help us understand. So if we have our reactants, we can basically use that mole ratio. If we have moles, we can use the mole to mole ratio to sit there and determine how much products we're making. That makes sense. We do it all the time when we're kind of scaling up in the kitchen, right? You normally cook this dish for yourself, and now you have a family of 50 that are coming over. You're going to scale up to sit there and make the adjustment. So it's going to be exactly the same concept that we do in the kitchen, okay? Okay, here's our next. How many moles of oxygen are required to burn 2.40 moles of ethane, which is C2H6? So the first thing that we need is going to be what?
Are given.
Are given. Come on in, let's grab it.
Which is 2.40
Okay,
moles of ethane.
I know it's just packed. Yes. But the first thing that we need is what? Before we do that,
Oh, the formula.
chemical equation, right? The chemical equation. So the first thing that we need is our chemical equation. Okay? It's like you came at the perfect time. Really? Yeah, so you can help us with our chemical equation. Perfect. So what type of reaction is this? It is an oxidation reaction, yes. Or we often will call it a combustion reaction, right? Burn, baby, burn. Okay, so we know that we have the hydrocarbon, which is our ethane. That's going to be one of our reactants. What is going to be our other reactant? We know that every fire needs oxygen.
What chapter again?
Chapters 6, 7, and 16.
Okay.
And we're going to make
Carbon dioxide and water.
is the chemical equation balanced? Somebody got their feelings hurt, and they found out that they were right.
6, 6, 7.
6, I'm sorry, 6. No, I'm sorry,
7,
7,
10,
10, and 16.
Okay. So I'm sure
7, 10, and 16. Yeah, we're struggling a little bit.
it's my fault. I got off of work and everything. I was trying to rush. Trying to put, see my scheduling. Exactly what I'm telling you right now. I got milk all pulled over me, so I smelled like horrible. I had to change real quick. It was bad. It was bad. Okay, my bad. That's right. What slide are we on?
33.
Thank you.
So we're going to use our CHO. Okay, so how many carbons?
2.
How many hydrogens?
6.
How many oxygens?
2.
On the other side,
1.
hydrogen,
2.
oxygen, 3. Okay, is that balanced? Okay, so how are we going to start?
Put a 2 in front of.
Okay, so we put a 2 here in front of the carbon. Okay, so then we end up with 2 carbons and 5 oxygens. Yes. Yeah, 2 times 4 plus that. Okay, balance. What's next?
Putting in 3 right there.
Okay, so then that would give me 6 hydrogens and 7 oxygens.
Have to put 7, what do you call it? What do you call it? 7, you split it at 7?
7 halves, yep.
7 halves?
7 halves, yep. 7 halves, or our fraction, okay? But we know that we can't have a half of a molecule, so then we're gonna end up multiplying everything by 2. Okay, so we're gonna end up with 2C6 plus, so 2 times 7 halves would just be 7. We have 4 CO2 plus 6 H2O. Is that correct?
Yes.
Okay, so now we have a balanced chemical equation. Right. Okay, so you told me now we needed to use our given, right? And our given is 2.4 moles. I love it when they ask me for moles, and we start off with moles. So we have moles of C2H6, and we want to get 2 moles of oxygen. How am I getting that?
For 7, for every 7 oxygens, there's 2.
So for every 7 moles of oxygen, and there's 2 ethans. Okay. Okay, piece of cake. Okay, report. Okay, so if we're given moles, we can just go straight from using the ratio to get the moles of what we want. But if we're given mass, we're gonna have to change the mass into moles by using what? Our molar mass, okay? And then we can use the ratio. And then we have to change moles back into mass to get the mass of what we're doing, okay? So let's see what. This is just basically showing you what we just talked about in a schematic. How many millimoles of nickel 2 chloride are in solution if 503 milligrams of silver chloride is precipitated in the reaction of silver nitrate and nickel 2 chloride solution? Okay, first thing that we need to do is what?
Break it down to
Break it down to a chemical, or break down a chemical equation, okay? So what is going to be our reactants?
nickel 2 chloride, so that's going to be Ag. Not Ag.
NiCl2.
Oh,
NiCl2. Okay, is that going to be solid, liquid, gas, or aqueous? Aqueous, that's right. And we know that because it says, okay, good job, because it says solutions. Okay, and what is our other reactant?
Silver.
Silver nitrate. Okay, so our other reactant is silver nitrate. So what is the chemical formula for silver nitrate?
AgNO3.
AgNO3. Solid, liquid, gas, or aqueous? Then that's gonna make, what type of reaction is this? 5 options. Swingers?
You said.
A swingers, a double replacement. Yes.
If you remember swingers, that's fine.
Yeah,
Double
we-
replacement. Okay, so who's hooking up with who?
And I is going with NO3.
Okay, so we have Ni hooking up with the NO3. And
Silver.
okay, so we know that the silver has what charge associated?
Silver has,
One.
A +1. That's right. Silver has a +1. And chloride has,
One.
chloride has a -1 because where it's located at. Where's it located at? What group? 17. We know that all group in 17 are always going to be a -1. Okay, so we have AgCl. Perfect, right? So it also tells us that 503 milligrams of silver chloride is precipitated. What does that mean?
Yes.
Forming
Solid.
a solid. You're gonna see me on the test. Okay. So our other compound is,
it's gonna be
we start with the positive. It's our positive charge. It's the Ni. And we know that it's, what charge again?
two.
It has a +2 charge. And we know that nitrate has what charge associated with it? -, that's right. So then how many will I need?
So two. That's right, that's Nicholas.
Okay, so if one of them precipitates, usually the other one is going to be in solution. And another way of determining that is if the other guy is always nitrate. Nitrate will always be aqueous. If it started off aqueous, it's going to end off aqueous. Nitrates. Group 1 metals. Group 1 metals, if they start off aqueous, they're always going to end up aqueous when they do a double replacement. Yes, it should be in, not organic, it's not inorganic, right? It's gonna be in the light. So it should be. If not, you can also use triptych. Okay, so is it balanced? Yeah. What do I need to do to balance it? Let's break it all down, but we can break it down since it's moving in units. Let's break it down in units to make it easy for ourselves. Okay, so we know that it's moving in the unit of, make our lives a little bit easier. Although it doesn't, it's not gonna make your life
I
easier.
can see, yeah, that color, yeah. Probably not.
Okay,
It's
so
okay.
of course I choose the color that you're typically colorblind.
Right.
So we have nickel. And then we have silver. We have chlorine. And then we have the 3 is moving in units. Okay, so how many nickel do we have on our reactant side? How many silver?
1,
How many chlorine?
2,
How many nitrates? On our product side, how many nickel?
1,
How many silver?
1,
How many chlorine?
1,
How many nitrates?
2.
Okay. Hey, you guys, I'll see where the 2 is. Good. Is it balanced? No. What do I need to do to balance it?
put it to AG.
AgNO3?
Yeah. E2 for AG.
Yeah. Okay.
Put it to AgCl.
Okay, is that right?
Yes.
Piece of cake. Okay, so now that we have a balanced chemical equation. Fire. Okay, so now we're ready to do the good work. Okay. So what is going to be my my starting point?
503.
503 milligrams.
So
And what are we trying to find?
milligrams of nickel chloride.
We want number of milligrams of nickel chloride. So this. Okay. Okay, so we have milligrams. So what are we going to do? Because we have mass, we're going to change that to moles. How do I do that?
Break it down.
Okay. So we're going to break it down. So we have how many silver?
1.
Silver weighs 108. Okay. And then we know chloride. $35.45. The silver 108 point what? Like 108.
It was
107.
107.
It's like 107.89 something.
7.
87.
Yeah, 107.
Okay. So we're gonna add them together. Something like that.
Got 104.
Oh, wow. 43.
Yeah.
I was testing you, testing.
0.32.
And so normally we say this is grams per mil. Okay, but we can also say that this is milligrams per millimole. Or kilograms per kilomole. Because when we do the conversion to go from milligrams to millimole, you're basically going to have 1,000 over 1,000. They're going to cancel each other out. If we go from kilograms to kilomoles, you're going to have 1,000. 1,000 is going to cancel each other out. Right? So
if the units, if the prefix are the same, then that value is gonna stay the same. Okay, does that make sense? Okay, so then I could just basically use 143 milligrams over 1 milli. Okay, so then millimoles are going to cancel out. And we're going to be, I'm sorry, milligrams are going to cancel out. We're going to be left with millimoles. Okay, but that's millimoles of silver chloride. How do I get to millimoles of nickel chloride? 2 millimoles of nickel chloride? Why do you say 2?
Because it was water, just cancel out, right?
But you're just using number 2. Why not 15? Why not 7? Why not 1? What am I going to use to sit there and determine the ratio going from silver chloride to nickel chloride?
Oh, wait, the. That's the top.
We're going to use our chemical equation, right?
Yeah.
So we're going to have to use the ratios of the coefficients, okay? So we have millimoles of silver chloride, so who should be on the bottom? Silver chloride. So we have, what is the relationship between silver chloride to nickel chloride? Okay, so we have 2 millimoles in the bottom. Of silver chloride to how many millimoles of nickel chloride? Or somebody said it under their breath. 1. That's right. Okay. Okay, so then that gets rid of millimoles of silver chloride. So then how do I get to the mass? Because isn't that what I want? I want milligrams. So how would I get
By the molar mass of nickel chloride.
Okay, so we need to multiply by the molar mass of nickel chloride. Okay, so how many nickels do we have in nickel chloride? Nickel weighs
59.
and we know that chloride, we have how many? That's essentially 70.9 together. Milligrams. Two. Wow. Okay. So what is our answer?
$227.9 or 220.
Questions? That is correct. That's right, Minty. We are using dimensional analysis to do the calculations. Okay. No questions. Good. Ready to move forward? Okay. Let's see. So the next thing that I want to talk is about percent yield or yield. Okay, so I have to tell a story first. 907, pretty good. Okay, so 907. It's a long day. Okay, so I was actually in undergrad and I was taking analytical chemistry. And you know, in general chem, and because I took general chem, I didn't have to take intro. Another story for another time. But anyway, it would have been my second year in college. And at this point, my first year was kind of flawless. I did fucking awesome. Grades were perfect, and everything like that. So, you guys know me. I have a big head, right? Little cocky, right? I'm not gonna sit there and lie. It's like shit. I got this. I own this. Chemistry is my game. Feeling confident, feeling myself, right? So I get in analytical chemistry. Analytical chemistry is basically you're doing a lot of analysis. So you'll start off with a reaction and you have to calculate how much you're producing, your yield. And then, or you'll use it to go back to figure out how much you actually started out with or the percentage and things like that. So we actually did this experiment and I had done all my calculations. And I go in and big head, and I'm really good. Like the lab, I own the lab. I know the equipment. I feel comfortable with the equipment. I'm not clumsy for the most part. And then, so I just go through it. Bam, right? And so, my partners love being with me because they just sit there and they watch me do it in action. I can do it. I suppose, I'm feeling really like into myself. So, I get in there. I'm like, bam, 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 bam. Okay. So then we calculate the percent yield. Now, if the reaction is done perfectly, you should get 100%. And I don't like getting of anything other than 100%. I'm shooting for the gold. I'm always shooting for 100%. I want to be perfect. I want to be flawless. I don't want to make mistakes. So the first time I do it, I'm like 82.3%. Something's wrong. So I'm like, okay, recheck my calculations, make sure everything's perfect again. Okay, so, and I'm quick, I'm faster than everyone else. Do it again. 82.1%. What? Hey, no. I don't get 82s. I get 100. Now, you may get 82, but I don't get 82. So I do it again. This is bullshit, right? 82.0%. Okay, so 3 times. 82.3, 82.1, 82.0. Something is fucking wrong. I'm confident I don't make mistakes. So I said, okay. So I looked at my colleagues' calculations. We have exactly the same calculations, right? They did exactly the same thing. And I said, okay, you do it, right? I do it. 82.4%. What the fuck, right? We're not getting 100%. So I'm getting a little upset. So I tell my lab partner, they're like, you're being anal. I'm like, I'm not being anal. It's 82%. That's a B. That is not an A. That's not acceptable. I want 100%, right? So I'm like, don't worry about it. You could take that
I'm gonna come back later because there's something that we did that just isn't right, right? And so I'm gonna figure it out. So, and I get hungry. When I get hungry, I can't think straight. I get moody and mean, and so I'm like, better go eat something because I'm already mad. I'm upset already, and I'm like, okay, this ain't gonna work. So I go to the cafeteria and I bring all everything out of the book, make sure, look at the chapter. Maybe there's the secret, that I overlooked or something like that. Go back over all my notes, do it again. Okay, so talk to the TA. The TA teaches 2 sections. One is in the afternoon and one is in the evening. So I went to his evening sections. And so I go in there and I don't need my lab because my partners, because I can do it all myself. Yeah, big head and everything. So I get in there. Now there's this kid named Jacob. Jacob is in our class and everything like that. Jacob is this rich kid who's, how do I say? He's a rich kid, everything has been handed to him. And so he's not dumb, but he acts dumb. You know what I'm saying? And it's like, he's so used to everybody doing stuff for him, right? And so Jacob finishes and everything like that. His group finishes. And then I asked Jacob, I'm like, he gets 100. I definitely do. This guy is not the sharpest knife in the drawer. So Jacob, what's your best get? Oh, we got 100%. All right, okay. So I got fucking 82 again. 82. I'm like, I am livid. This motherfucker who is dumb as a box of rocks gets 100% and I get an 8. Hell no, that is not gonna work. So I go through and I do it again. I get the same answer. Do it again. I get the same. But Jacob told me they got 100%. No, Jacob is dumb. They never get 100%, right? So what the fuck? What did I do wrong? So I do the thing, and I'm slightly, I can't say I'm truly religious, but I'm partially religious because my family were religious. So I'm bringing some of this over with me. And I'm like, God, is this a sign? Now tell me, make sure that this is right and give me that 100% and everything like that. And then I said, if I get 82%, I am done. You're telling me that this is not what I'm supposed to do, right? So I go and I do it one more time. 82.3%. Motherfucker. I am livid. And I have a quick temper. That was young, quick temper. I still have a quick temper, but I controlled it a little bit better than I used to. I get so fucking mad. I throw my lab book, because we had lab books. You know how you guys get these handouts and you upload the handouts. We had these big ass fucking lab books. Throw my lab book across the room into the garbage can. And I am pissed. So I get all my stuff. I kick the fucking garbage can as I'm going out, slam the door, and the TA is just watching me like, what's this kid doing, right? And he's just watching me do this. And then he goes out and he's like, Mr. Henry, what the hell's wrong with you? I got 82.3%. And he laughs, right? He just starts cracking up. And I'm like, this motherfucker is laughing at me. At this point, I want to fight, right? Don't you laugh at me, right? And then I'm like, so I am pissed and trying to keep it in and not be violent. And I want to sock him in his jaw. Mr. Henry, why don't you come with me? Right? So we go. And he says, so you know exactly what you're doing. He says, you started with this experiment. The purpose was to recover what you started off with. He says, do me a favor. Read this bottle. Bottle, and it says molecular compound, blah, 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 and it says 82.3% pure. So, there's a moral behind this. When we talk about percent yield, you're never going to get 100%. And if you get 100% yield, you're full of shit, right? Jacob was full of shit, right? Because 99% of the time, you're working with substances that is impure. It's really hard to get a totally pure substance. And if you do have a totally pure substance, you're probably working in industry and you have to pay out of the nose to get that substance, right? So if you look at Fisher Scientific, you're going to get 98%, you're going to get 97%, you're going to get 82%, right? It's very rare that you get 100%. And if you're getting 100%, you better pay, you're going to be paying like $1,000 per gram of that substance to get it that pure, right? So, moral of the story is, don't listen to idiots, right? Secondly, always assume that you're never going to get 100% pure.
It's never gonna be perfect. And the other thing, don't make pacts with the devil, or God, whoever, to sit there and try to decide your fate. You decide your fate, right? So the thing is, I had a lot to learn. And that was a little bit of humility, for one. To also sit there and ask questions when you're in doubt and you don't get the answer that you think you're gonna get. Is this right? Is it okay? Is it okay for me not to have that? Don't make the assumption that 100% means 100% frankness. So when we talk about percent yield or ideal yield, right? It's ideal. Ideal is what we're going to be calculating. This is under the perfect circumstances. Everything is perfect. You got the perfect chemical. The reaction is perfect. There are so many ways the reaction can go wrong. You got a lot of side reactions that are happening. So you're never going to get 100% yield. Sometimes you may get over 100% yield. That's usually because, it's not fell into your solution, or, you were talking and a couple of spitballs came out and stuff like that. So it weighs a little bit more than what you're anticipating, right? But you're never going to get 100%. Something is always going to be a little bit wrong because you're never working with something that's so fucking pure, or the equations. There's always side reactions. Okay. So we have what we call our ideal yield. That's what we're calculating. And then we have what we call our actual yield. That's what we actually get. Okay. And it's important for us to distinguish between them. So we use the percent yield to sit there and distinguish how much of it that we actually got. So if you end up with 100% yield, that means you've got everything back that you're supposed to get, right? If you don't got 100% yield, that means that there's probably some impurities in there. Or occasionally it is human error that we make a mistake and knock shit over and spill things in there, And then you already know if you get more than 100% yield, you probably dropped a hair in there or something like that, okay? And so it's important. It tells us a lot about things. So you want to be able to calculate percent. And it's really easy. It's just going to be your actual divided by your ideal. Ideal is what you should be getting if everything was perfect. Your actual is usually less than your ideal, okay? So let's test this out. A solution containing 3.18 grams of barium chloride is added to a second solution containing excess sodium sulfate. Barium sulfate precipitates. Calculate the ideal yield of barium sulfate if the actual yield is 3.37 grams. Where's our first step?
I would guess. Fine, more mass.
Step back. What do we need? We can't figure out how much of anything we're making if we don't have. We need a chemical equation. That's our first step. So let's do that first step. What are our reactants?
Barium chloride.
Okay, chemical formula for barium chloride.
BaCO2.
Okay, was that a solid, liquid, gas, or aqueous? Yes. That's right. Okay, what is our other reactant?
Sodium sulfate.
Okay. Okay, so what is the chemical formula for sodium sulfate?
Na2SO4.
Solid, liquid, gas, or aqueous? That's correct. Okay. what is our product? So what type of reaction is this?
Double.
Replacement. Double replacement, that's right. Okay, so who hooks up to who?
Yeah, it's gonna go with it.
SO4.
So,
And
CL is gonna, oh, NA is gonna go with CL.
so, sodium has what charge? And, and Cl has what charge?
-1.
Perfect. And we know salt is soluble in water, so it's going to aqueous. Okay. Barium has what charge? Sulfate has what charge? Okay, so we need one of each. Is that going to be solid, liquid, gas, or aqueous?
That'd be solid
It's going to be solid. Why is it solid?
because it precipitates.
Because it precipitates. Okay. Is it balanced? What do I need to do to balance it?
Add a 2 in front of sodium chloride.
Okay, so it's balanced. We're good to go. Okay, so what's our given? Our first given.
3.18 grams of barium chloride.
Okay, so we have 3.18 grams of barium chloride. Okay, so what do we need to do next?
Per mass.
Need some more mass. Barium weighs
137.
chloride. 2 of them. So 35.45 times 2. Eight. Roughly. Okay, so I have 2.8 grams per mole. So how do I get rid of my grams? Joy at the bottom, grams, 1 mole on top. That's barium chloride. What are we looking at? What are we trying to solve for?
Barium sulfate.
Okay, we're trying to solve for the barium sulfate. So what is the ratio of barium chloride to barium sulfate? Or 1 mole of barium chloride.
One.
Like it. It's like easy. Okay, so now I have just moles of my barium sulfate. So how do I get to grams of barium sulfate?
Molar mass of barium sulfate.
Okay, so we need to find the molar mass of barium sulfate. So we know that we have how many bariums in barium sulfate? That way, 137 from earlier. We have how many grams for sulfur? I mean, how many sulfurs do we have for barium sulfate?
Four.
How many?
One.
We have one, right? 4 is for the oxygen, right? So for the sulfur, there's only one, and it weighs how much? 32. And how many oxygens? How many oxygens?
4.
So we have 16 times 4. That's oxygen weighs 16. And so we add them all together. 233. Okay, so 233 grams barium sulfate. One mole of barium sulfate. .56 of barium sulfate. Okay, so this would be my actual, or is it my ideal? Your actual.
Ideal.
Sorry. Right, it's what we calculated. So the calculated one is going to be our ideal. Okay, so if it's my ideal, yeah. So then how do I calculate the percent yield? They tell us if our actual is 3.37 grams. So what's the equation for the percent yield?
Actual divided by ideal.
Okay, so that's actual divided by okay, so then that's gonna equal, in this case, our actual was 3.37 divided by 3.56 grams. Unfortunately, 94.6%. Did you guess that?
Yes.
Good. Jeremy, you good?
Yep.
Dale, are you good?
Yep.
Moving forward. Yep. Good, good. That's clear. Lauren says she's good. Okay. So the next thing that we're going to be talking about is limiting reagents. Brenda's good. Good. Okay. Okay, so the next thing we're talking about is limiting reagents or limiting reactants. Okay, so how many of you guys have made cheese sandwiches? Grilled cheese sandwiches. It's a rough day. It's been a long, long day. Got up really early to get coffee at Panera's and Dunkin' Donuts.
Damn.
Oh, we went all out. Only the best. Only the best. We had Starbucks and Panera coffee.
Wow.
Damn. So you guys make grilled cheese sandwiches?
Yes.
Okay, so this should be real easy. Okay, so let's write the chemical equation for a grilled cheese sandwich. Just the basic grilled cheese sandwich. We're not gonna make anything fancy. Okay, so basic grilled cheese sandwich is gonna be 1 slice of cheese, 2 pieces of bread, and that's gonna go our sandwich, right? So 1 slice of cheese. Plus 2 pieces of bread. That's gonna be 1 sandwich. Okay, so let's say I have a little bit of party, and I'm a little bit of a party, and I'm gonna invite, a couple people over. I'm gonna make grilled cheese sandwiches for them. Okay, so I get a loaf of bread, and it has 20 slices of bread. And I get a pack of cheese, and that has 20 slices. Okay, how many sandwiches can I make?
10.
10. So I know that I can only make 10 because I have 20 slices of bread. You know the relationship between my bread and my sandwich is a 2-to-1. So it's 2 bread to 1 sandwich. And that would be 10 sandwiches. Okay. So how many pieces of cheese did I need for those 10 sandwiches? I needed 10. So I only needed 10 slices of cheese. How many do I actually have? 20. So who would be in excess? My bread or my cheese? Cheese. That's limiting reactants. one of your products are limiting, you run out of it, or the other. Pretty simple, right? Okay, so let's get started. What's that?
You can double up the cheese.
Double up the cheese. We've got some really good sandwiches instead of cheap ass Dr. Henry sandwiches.
Sorry.
It's okay. We're working on a budget. You know, we gotta save that cheese for the next part.
Right, you know what, you're right.
Tell them to start paying me more and I'll give you guys more cheese. Okay, so this is just basically showing us that same concept. So here we have 3 carbon. We have 2 oxygen molecules. So when we bring it together, our carbon and our oxygen, we're gonna end up getting 2 carbon dioxide and 1 carbon that's gonna be unreacted. So who's in excess? Because that's what's left over. Right? Simple, right? So just like those cheese sandwiches, this is exactly the same thing that's going to be happening in the case of the okay. Okay, so let's do that hard part now with calculations. So it says calculate the mass of antimony 3 iodide, Sp3, that can be produced by the reaction of 129 grams of antimony and 381 grams of iodine. Also find the mass in grams of the element that would be left. Okay. So that's going to be our very first thing that we need to do. Make a chemical equation. Good job. Okay, so what are my reactants? Okay, so what is the symbol for antimony?
Yes.
Sp. And then our symbol for iodide?
I.
Is it just I?
I2
I2. Why is it I2?
polyatomic.
Because it's diatomic?
Oh, diatomic.
It's diatomic.
Yeah.
Polyatomic means it has more than 2. Yeah. Okay, so what are we making? What are my products? My bad.
Antimony.
SB. Right. Okay. So we have our chemical reaction, right? But what type of reaction is this, by the way? Combination.
Which is on it, bro.
And she's like, I'm gonna go home.
Go guys.
Okay, is it balanced, by the way?
No, I lied.
Stop lying to me.
I'm sorry, I'm trying to keep your toes.
Okay. Can't use my answer, that's all right. Okay, so how many antimony do we have on our reactant side?
1.
How many iodine? On the other side?
Trace.
Okay, so what do I need to do to balance it out?
A little 7 thing, aren't we? Oh, you really could just put a 2 in front of the I on the reaction side. I mean, sorry, I didn't say what 3.
Okay.
And then put a 2 in front of the I.
And one in front of what
I forgot what the side's called.
product side?
The product side, yes.
So am I putting it in front of the product side or just the I?
Just the I.
Are you sure? Can I do that? Is that legal?
No, actually, I think
Why isn't that legal?
it's
Because,
part of the anatomy.
yeah, so it's a compound and they're together. So then I have to put it in front of
The whole thing.
the whole thing. That's right. So then how many antimony do I need?
Two.
We're balanced. Okay, so now that we have a balanced chemical equation, what are we gonna do? Okay, so this is the secret. This is how you always know that you have a limiting reactant type of problem, is when they give you, both your reactants give you a value, right? Because we have 129 grams of antimony, and we have 381 grams of iodine, right? Both of those are reactants, right? So that basically means that I have to calculate the number of moles for each one of those. So here we go. So I'm going to show you the surefire way of figuring it out, okay? And then I'll show you the other way of figuring it out. So the surefire way is the long way, okay? So we have 129 grams of antimony. Okay, antimony weighs
122.
Okay, so what is the molar ratio of antimony to the antimony iodide? Calculate that.
1 to 1.
So 1 to 1 or 2 to 2, right? 2 moles of SB. Yeah, 2 moles of SPI3. Okay, and then how do I get the number of grams of the antimony iodide, antimony 3 iodide? Okay, so we need to find the molar mass. We said antimony was 122. Iodine, we have 3 of them. Iodine weighs how much?
127.
By that times 3. I vote 3 grams per mole. Same picture we have. Okay. So there's a law. Can anybody help me out with this law? There's a law that we definitely apply in this situation. Bless you. In this situation. Yeah, starting at the very beginning of the semester.
Conservation.
The law of conservation. So the law of conservation says what you put in, you've got to get out, right? So that means how much mass you put in, that's how much mass you should be getting out of school too, right? Okay, so how much mass, what is the total mass that we put into our reaction? How would I calculate? Well, let's add up what we're putting in. How much anthony did you put in?
129.
Okay, so 129 plus 381. What is that?
510.
510, and we get out 532 grams. So that probably tells me that the anthony is that excess or is that limit?
Excess.
It's excess. Okay, so now we've realized that this guy is excess, so we can't be using that one. So that means that we have to be using the iodine. Okay, so we know that the iodine is 381 grams. And what is the formula for iodine? Yeah. Okay, so we know that iodine weighs 127. We'll multiply that by 2, so then that's what, 254 for 1 mole. And the ratio of iodine to anthony iodide. Anthony iodide.
Three iodine to every 2.
So we have 3 iodine to every 2 moles. of it. We know that the anthony weighs 503. Calculated that earlier. And that's pretty good. So that math.
Okay. So this is how much anthony that we have. You also take a look, this value is lower than the other. That's the one you're always gonna look at, that's the lowest value. Okay, we know that altogether, you told me it was 510 grams total. We also know that it was the anthony that is in excess. So if we subtract 510 minus 503. That's going to give me 7 grams of SB. That will be left over.
What's between 510 and 502?
What was that?
So what's between 502?
Oh, it says total.
Okay.
So that's total grams. So 510 total minus
Oh, got it.
503 grams.
Got it.
So. and we know that it was SB that was in excess. Okay, so that's the long way. Surefire. Both, the money gives it the less value. Okay. I think we're gonna have to stop there. Okay. We'll come back and show you another way. Not you guys, the other groups, yes. They don't finish till 4 weeks left.
Oh, wow.
You're done next week,
Yeah.
and then they won't be done until 4 weeks after.
Oh.
I'll figure it out. How that happens.
Did you all start at the same time? They have a long spring break.
Okay, so that's it. That's all. Any questions? Brenda, Lauren, Carol, Fidel, Edgar, Mitzi. Are you guys all good
Good for now.
now?
You're the only two that showed up.
I'm good.
We're good?
I need to take credit.
We're done.
Okay. I will see you guys Monday. Monday.